talking about temperature, right? You would think that that would be the first thing we talk about. But it turns out that this depends on many other things that we needed to cover. We needed to cover greenhouse, we needed to cover atmospheric convection and clouds, and now we can talk about warming and temperature changes in general. So let's go through an overview of what's happening today. So first of all, here is the global mean surface temperature. You can see the difference between the previous estimate, AR5 was 2013, and AR6 is the one from this year. This is the IPCC estimate. You can see that the warming so far is about 1.2 degrees. So there's a big jump between the previous one and the current one. Look at the difference at the end of the time series between the orange and the blue. So something happened during these last almost 10 years. It's pretty significant. Okay, so these are the things we'll cover today. First of all, polar amplification. So what you see here is the warming by 2100, estimated by a model as function of latitudes. So you see a very large warming in the Arctic, somewhat enhanced a warming in Antarctica, and some middle type of value for the low latitudes. Right? So the thing you see here mostly is the polar amplification. That is the idea that the Arctic in particular warms much more than the global mean. Is it clear on this picture, on this figure? All right. So that's the one thing we want to understand. Next thing we want to understand is these periods of hiatus. So you see that there are two periods that are marked by horizontal lines. That one and this one, where it seemed like global warming stopped for a few years, maybe even for a few decades in the first case. And we want to talk about why this happens and what does it tell us about the physics of global warming in general. So that's number two. Then there's the issue of the effects of the ocean. So it turns out that the ocean, because it has such a large heat capacity, slows down the warming that we feel. So you see here two pictures. One is the temperature as function of time, going all the way to 200 years, if the ocean were shallow. So you see a rapid decrease within 25 years. By year 50, the temperature, the warming is already 3 degrees. And the second estimate is if the ocean is deep, as it really is, 4,000 meters. And in that case, you see a rapid increase at the beginning, but then it takes between 1,000 and 2,000 years to get to the same 3-degree warming that we saw before. So the ocean delays the warming, and we want to understand why that is the case. Okay, and finally, there's the issue of stratospheric cooling. So, this is the troposphere, the lower part of the atmosphere. The upper part in this figure is the stratosphere, and this is a projection for, again, 2100 minus pre-industrial. So you see very strong warming in the lower atmosphere and very strong cooling in the upper atmosphere, and we want to understand why that happens. So that's the outline for today. These are the 4 subjects we want to cover. All right? So just a few words on what we've seen so far. So you see here the difference between the land and the ocean. So the warming over land the average is actually 1.6 degrees roughly, while over the ocean we have 0.9 degrees. So the oceans warm less than the land. We'll talk about why that is the case. And then this is a decadal estimate of the warming, and you can see that the last few decades, the last 4 decades, are pretty consistent in increasing temperatures, maybe even accelerating warming. Okay. So let's see. Here's the warming from 1900 to 1980. And the reason I'm showing that is mostly for these white areas here. White areas are places where we don't have enough data, so there's a large uncertainty there, and they're therefore drawn in white. Okay? This clearly, no one was measuring the temperature in this area in the Southern Ocean or the Pacific in 1900. So you'd have to use some sort of extrapolation to find what the temperature was. In this case, the people who drew that preferred not to extrapolate, but just to leave it as empty. And this is the warming from 1980 to 2020, for which we have plenty of data, even satellite data for much of this period. And you can see the warming, and you can see the polar amplification in the warming that already occurred, right? You could see that this is higher than the rest of the globe. Okay, so we see here the uncertainty and the polar amplification. Any questions about these? Okay. Okay, here's the next one. So you look at this. This is the global warming curve, and these two periods. And if you're a climate skeptic, you get really excited because from 1998 to 2013, for 15 years, the global mean surface temperature did not increase. And that obviously is interesting. So we want to understand why that is the case. Fox News was especially excited about this, 2015. And they're saying, is the government tinkering with global warming data? So I prefer not to tell you what the answer is. I want you to now jump to this section, even if you didn't finish the last one, and think about this issue and try to explain yourselves why there was a hiatus in global warming. Yeah, you can see how similar it is. This is the actual observed record. And this is the record you get from natural variability alone. This is the results of a climate model run without increasing the CO2. The temperature goes up and down, and then when you add a linear trend, you get these two plateaus. Whenever the climate was trying to cool, given the linear warming, you get a plateau. So that's exactly what you'd expect. Okay, so let's see. Let's talk about hiatus for a second. So here's the observed record. Here are the two hiatus periods. This is when people were especially excited about this because we were in 2015 or so. The temperature was flat for about 15 years. Seems like something wrong was going on. Then clearly, if you look at the temperature now, you see this big jump that happened over the last decade or so. And this animation is especially beautiful. Look at this. So what we're seeing now here is 1998 to 2012 showing the plateau. And now this animation will zoom out and we'll see what happened. So you see a plateau if you focus only on that area. And here's the trend that you see, that there's not much trend here. This is the increase before this. And that's the increase after that. So there's no question that there was no pause in global warming, and we understand that these plateaus are a natural consequence of the combination of a warming trend and natural variability. Okay, so now this is a useful figure to get us to the next point. It's difficult to see from where you are, but what you see here is we have radiative forcing, so a certain number of watts per meter squared that are trapped by greenhouse gases and don't escape to outer space. What happens to that heat? So this shows us that all of this cloud is heat absorbed by the ocean. And then the rest is any other component of the climate system. You see some goes to melting ice, some goes into the land, some goes into the atmosphere. Basically, all of the heat goes into the ocean. So what are the consequences of the fact that the heat goes into the ocean is what we're trying to figure out. And there are going to be a couple of consequences. As you'll see, one, the atmospheric warming is slowed down. We'll see how that goes. And so these are the presumed consequences in the popular press. So you always have to be careful, but the New York Times at least claims that there's marine species are at risk. The habitats are changing. Okay, so we do want to understand what is the consequence of the fact that the ocean is absorbing all of that heat. So let's start from this. So if you look at the CO2 equivalent mixing ratio, that is the equivalent CO2 concentration that takes into account all greenhouse gases. So even though CO2 is only at 420, the equivalent CO2 taking into account all greenhouse gases is about 500. So it's almost doubling. If it's doubling, you expect a certain warming, say 3 degrees. That would be a mid-range warming in the IPCC estimates. So, and we know that the warming is logarithmic in CO2, right? We covered that. So we can write a law like this, that the warming is equal to 3 times log 2 of the CO2 divided by 280. So if the CO2 concentration is 560, which is twice 280, we would get 3. But because it's 500, we're getting 2.5. So we would have expected the warming now to be 2.5 degrees. Instead, it's only 1.2. So we only saw half of the warming that is expected for a CO2 concentration of 500, which is, again, equivalent CO2 mixing ratio, which is what we have right now. So, and the reason is that the ocean is slowing that warming, and we want to understand how that happens, okay? So we'll do two things now. One, we'll see how one can calculate these 3 degrees warming. So that is the expected warming of the climate system once in equilibrium under doublings of CO2. We'll see how to calculate that without a climate model, very straightforward. And then we'll see how the ocean slows down this warming that we expect. By the way, given that, if we stop now and drop all emissions to 0, do you think there's a way for us not to go over 1.5 degrees? It's just a question of time, right? The climate system warms, the ocean, which is slowing it down, will warm slowly. And we should be getting to 2.5 if you believe the estimate of 3. But even if the 3 is very far off and it's only 2, we'll get to 2, even with 0 emissions, as long as the CO2 is not reduced in the atmosphere. So there's really no way to remain under 1.5. I think, I hate to be pessimistic, but I think it's pretty obvious. So the subject is equilibrium climate sensitivity. What we're trying to do again is estimate the warming that we expect for doubling of CO2 without using any climate model, based mostly on observations. So for that, we need the heat budget of the surface, and it will be something like this. So delta Q now, I'll explain everything in 1 second, equal to delta F now minus lambda long wave times delta T. Okay, so what do we have here? I'll give you a second to catch up. Okay, so radiative heating is the heat trapped by greenhouse gases. Some of this heat will escape to outer space simply because there's some warming. As a result of the warming, black body radiation, remember sigma T to the 4th, will get larger, and that will lead to some of this heat escaping from the atmosphere. And we represent that approximately as some coefficient that we don't know, lambda long wave, that is something that we don't know, times the warming itself. And then the difference between, this is the heat being trapped, this is the heat escaping, the excess heat escaping, and this is what's remaining, this goes into the ocean. So what do we know? We can measure this because we know how much warming in the ocean has occurred, so we can deduce these fluxes. We know what the radiative forcing is. That's a relatively simple calculation. And we don't know lambda, and we know how much warming happened by now. So let's call this T now. Okay. And from this we deduce, before we deduce anything, in a steady state, for doubling of CO2, the balance is simpler. We have 0 equal to delta F times 2 minus lambda long wave times delta T times 2. I'll explain this in a second. This is top of the atmosphere. This is long wave at the top of the atmosphere. This is the heat escaping from the atmosphere due to the warming that has occurred. Okay, so in a steady state, where the ocean has completed its warming, it doesn't absorb any excess heat, right? Because as long as it absorbs excess heat, it keeps warming. Now we're asking what happens when the ocean completed its equilibration to CO2. So it doesn't absorb any more heat, and therefore delta Q would be 0. So then we have a budget of, this is the radiative forcing for doubling of CO2. It's again something that we know, we can calculate. And this is the heat escaping out of the atmosphere, at the top of the atmosphere, due to the warming at double CO2. So this is the budget today, and this is the budget once this climate system is equilibrated. What we're looking for is this. What we don't know is this. Okay, so how do we do this? So we can deduce from the equations we wrote that delta T 2x, the warming after doubling of CO2 and equilibration, is equal to delta F 2x, the radiative forcing, divided by this lambda that we don't know. And we can also extract lambda from this equation. So let's connect this one to that. And this tells us that lambda, long wave, is equal to delta F now minus delta Q now divided by delta T now. All of these are quantities that we do know right now. So we have an estimate for lambda. We can substitute in the first equation, and this gives us an estimate of the warming. So the warming is delta T at double CO2 in equilibrium is equal to, so delta F 2x, the radiative heating for doubling of CO2, times delta T now, divided by delta F now minus delta Q now. I'll give you a second to copy it, and then I'll explain again everything. Okay, so the slide summarizes everything, so let's look at it again. This is the heat budget of the ocean right now. We said this is the amount, delta Q is the amount absorbed by the ocean. That amount is equal to the radiative forcing, how much is escaping, minus how much is escaping. So the excess heat flux into the ocean is equal to the radiative forcing minus the top of the atmosphere outgoing long wave radiation. Any questions about this first one? Okay. We said that at equilibrium, the ocean doesn't absorb any excess heat because it stopped warming by definition at equilibrium. And then delta Q is 0, but we have radiative forcing balancing the heat escaping from the top of the atmosphere, from the revised, well, let's just stop there. So this is the heat, the budget is the radiative forcing balanced exactly by the excess heat escaping at the top of the atmosphere. So we can extract from the second equation this relation, and we can extract from the first equation this relation, and now we can write delta T2x is equal to this. So what do we have in this expression? This is the radiative forcing at 2 times CO2. This is the warming that has occurred now. We know that. We know the radiative forcing as function of CO2. That's a relatively simple calculation. Doesn't require a complicated global climate model and so on. This is the radiative forcing now, which we know, and this is the heat going into the ocean now, which we know. And the bottom line is you use all of these numbers and you find that the warming is 3 degrees, which is consistent with many other ways of estimating the expected global warming at the doubling of CO2 in equilibrium. So this is referred to as the equilibrium climate sensitivity, the warming that would have occurred at double CO2 if you let the system equilibrate. So given that the ocean is warming, what is the structure of the warming in the ocean? So here's the global curve. You see here temperature, degrees per decade. So this is warming rate. And this is depth. The mean depth of the ocean is 4 kilometers, but there are areas that are deeper, obviously. And you see that the warming is mostly in the upper ocean. Note that this starts at 1 kilometer. So it's already the deep ocean that we see here. You see that the Southern Ocean warmed more than most of the ocean under 1 kilometer. We'll see in a second why. But the warming is, say, 0.05 degrees per decade. It's pretty slow. It takes a lot of time for this heat that we're generating in the atmosphere to penetrate into the deep ocean below 1 kilometer. It's clear from this rate that is not large, but clearly something is happening. This explains what are the processes by which this heat gets carried into the ocean. So let's see. What you see here is two sections, one in the Atlantic and one in the Pacific. So in the Atlantic Ocean, you have, this is the North Pole, this is the South Pole. And you see water sinking at the surface and going south here. This is known as the North Atlantic deep water. When you hear about the meridional ocean circulation, that's part of that. So if you warm the surface here, this warming will penetrate all the way to a depth of about 2.5 kilometers. That's one mechanism by which the warming penetrates. In the Southern Ocean, the warming extends. The water that sinks at the surface is even denser. You know, there's cooling in the Southern Ocean. The atmosphere is very cold. You cool the water, and it sinks all the way to the bottom. And if you warm this water here, it will carry the heat all the way to the bottom. But it takes a long time to then propagate toward the rest of the ocean. You see here again, water sinking near Antarctica in the Pacific and propagating northward, advecting the water northward. And so you can imagine that the Southern Ocean will warm in the deep area faster because there's this direct link to the surface, and the surface is the one that feels the warming mostly. Does that make sense? Any questions? So this is the oceans, the meridional overturning ocean circulation. This is one of the important mechanisms for the heat to actually penetrate the deep ocean. In addition to that, there's just mixing here. But that mixing is not very effective. It does work as well, but it takes a long time to mix heat from the surface that is warming due to the greenhouse gases all the way to the deep ocean. Okay. So I think we can go to a workshop again. What we're doing next is trying to understand the effect of the ocean slowing down the warming that we feel. Let's look at the final result, and then we'll try to understand what's going on, and then you'll be doing this calculation yourself. Some of you, I noticed, already did it. So again, these are two scenarios. One in which you assume that the ocean is only 40 meters deep, and the other one is more realistic, where the ocean is 4,000 meters deep, 4 kilometers. In the first one, where the ocean is only 40 meters deep, so the surface ocean is 40 meters deep, and the deep ocean, in quotes, is also 40 meters deep. You see that there's warming of the surface and warming of the deep ocean. Then they pretty much go together, both of them, the deep warming and the surface warming. And by 50 years, we're settled on the assumed climate sensitivity of 3 degrees. This scenario assumes that the climate sensitivity, the equilibrium climate sensitivity is 3 degrees. This is the case where the ocean is much, much deeper. The deep ocean is much deeper. So you see, first of all, that after about 75 years, the surface has only warmed by less than 2 degrees, same radiative forcing as the other one. And the deep ocean hardly warmed. If you look after 2,000 years, both of them have reached 3 degrees warming. So the fact that the deep ocean is massive and remains cold for a long time prevents the surface from warming and keeps the temperature below what you'd expect from equilibrium climate sensitivity. And that is the effect that we're seeing today. We're seeing, as we discussed at the beginning, that we only saw 1.2 degree warming, even though the CO2 is such that it would have justified twice as much warming. So what we want to do now is understand this. And the way we're going to understand it is by writing an equation for the surface ocean, which includes the atmosphere, and for the deep ocean. We'll write two equations and analyze and solve them, and then we'll get this. Any questions about what I just explained? Okay. So The subject is referred to as transient climate sensitivity now. This is the actual warming we see as the CO2 increases, as opposed to the equilibrium warming that we'll get until when the ocean finished warming up. So for that, we need to write two energy balance equations. So here's the heat capacity of the surface. By that, I'm referring to the upper 40 or 50 meters of the ocean, so the surface ocean, times d delta T surface dt. So this is the rate of change of the ocean upper temperature. And there are going to be several contributions. So first of all, radiative forcing, delta F2x. So suppose we're starting with a scenario where there was no radiative forcing, the warming was 0, and then suddenly we jumped to twice the CO2. So the radiative forcing from T equals 0 is the radiative forcing of doubling the CO2. So a few watts per meter square. And then we have, as before, we have cooling to outer space, parameterized as before. So lambda long wave times delta T surface. So this is heat escaping out of the atmosphere. And the new term is this, minus gamma delta T surface minus delta T deep. So what does this stand for? Well, as long as the surface warmed and the deep ocean did not warm, this term is, with the minus sign, is negative. So it has a cooling effect on the surface. You could think about this as the surface mixing with the cold water that hasn't warmed up yet, and therefore this slows down the warming. So this is the effect of the communication between the upper ocean and the deep ocean. This is the effect of that on the deep ocean, on the surface ocean. Make sense? One more second. So once the deep ocean has finished warming, we'll see that this term vanishes. Ian?
What is the gamma?
Gamma is some coefficient that represents the strength of the communication between the surface ocean and the deep ocean. Okay, and then we need a heat budget for the deep ocean. So we have C deep, that's the heat capacity of the deep ocean, times d delta T deep, the warming of the deep ocean dt. So this is the rate of warming of the deep ocean. So together, the heat capacity times the rate of change of the temperature gives you a rate of the change of the heat content of the deep ocean, per meter square, by the way. And that's equal to gamma delta T surface minus delta T deep.
Are the heat capacities between the surface and the ocean that much different? I thought that it would just be a property of it being seawater.
Right. The difference is that the heat capacity is a product of the heat capacity of water times the depth of the ocean. So this is only, say, 40 or 50 meters deep, but this is 4 kilometers deep. So this heat capacity is much bigger as a result of that. It's not the inherent heat capacity of seawater. It's actually the heat capacity of the entire column of water. Nice question. Okay, now let's see. I want to explain this term again now. So suppose the surface has warmed, but the deep ocean has not warmed yet. This term would therefore be positive, right? This has warmed by 1 degree. This is 0.01 degree. So this term is positive. So the deep ocean is warming as a result of the mixing with the upper ocean that is warmer. Very simple. In this case, the term is negative because of this minus sign. And therefore, as long as the deep ocean is colder, this causes cooling at the surface that prevents us from getting to the equilibrium mixing, climate sensitivity. At steady state, you could immediately see what happens. Steady state means that ddt is 0, right? So let's do this in a different color. So at steady state, ddt is 0, so this would be equal to 0, let's write here at a steady state. So a steady state is once the ocean has finished warming. This could take 1,000 years, maybe 2, maybe more. When that is the case, the consequence is that the delta T surface is equal to the delta T deep. That's a very idealized, simplified model and so on and so forth. But in this picture of the ocean being divided into 2 layers, the consequence of a steady state is that the deep warming is equal to the surface warming. When that happens, this term vanishes too, so we can delete this term here. This goes away because we're at a steady state. And we get from that, again in steady state in blue, that delta T is equal to delta F divided by lambda. So these are all the equilibrium values. This is exactly the solution we had before for equilibrium climate sensitivity. So this picture is consistent with what we did before when we didn't take into account time rate of change and so on and so forth. And deep ocean, eventually, when the ocean equilibrates, we get the same warming as before. This is T surface here. Questions about this? All right. Let me show you the same thing again now. So what do we see? This is the heat budget of the surface ocean, the upper 40, 50 meters. And we have radiative forcing. We have the outgoing long wave radiation that's escaping because there was some warming. As soon as there's some warming, the long wave radiation, the black body radiation is larger. That's reflected by this term right here. And then there's the mixing with the deep ocean that we discussed. So that's the first heat budget. The second heat budget is the deep ocean showing this mixing term again with a minus sign. So whatever the surface is losing in terms of heat, the deep ocean is gaining. There's heat conservation, right? That's the meaning of these terms being the same. And you can see how the surface and deep heat capacities are calculated. You have the density of seawater, the specific heat capacity times the thickness of the layer. So this is H being 4 kilometers, and this is H being 50 meters, just the upper ocean, for example. And then, as we said, in a steady state, if we set DDT to 0, we get this, which is consistent with what we had before for equilibrium climate sensitivity. So now we want to talk about polar amplification. So why is it that the warming is enhanced at high latitudes? So this is from this paper, and you can see an estimate of the warming, roughly 4 or 5 degrees in most latitudes. But in the North Pole, you get this warming of 15 to 20 degrees in the Arctic. That's a huge effect. So we definitely want to understand why that happens. So think about permafrost melting, sea ice in the Arctic melting. This has many consequences that we care about. Okay, so there are several feedbacks that are important here. So we're going to cover 3 different mechanisms, if I remember correctly, that lead to the fact that the Arctic is warming more than the mid-latitudes. The first one is kind of obvious. There's the albedo feedback. By that we mean, suppose we melt some sea ice. Sea ice is normally reflecting shortwave radiation during summer months in the Arctic. And as a result of that, the result of the sea ice melting, more heat is absorbed by the ocean. This leads to more warming of the ocean, and this leads to further melting of sea ice, right? So melting of sea ice leading to more or less reflection, first of all. Of shortwave, more absorption, by the ocean. And as a result of that ocean warming, and ocean warming implies more sea ice melting. We have a chapter about sea ice, and we'll see what happens, but basically this leads to a very dramatic sea ice and very dramatic warming of the ocean just because of this positive feedback. Remember, we started with melting, we ended with enhanced melting, so now we go back here. So even more melting means even less reflection, even more absorption, even more ocean warming, and even more sea ice melting, and this reinforces itself and amplifies whatever trigger this had due to higher CO2 initially. And so this would lead to a significant warming that didn't happen in the mid-latitude because there was no ice there to begin with. Okay? And if the temperature, if this is the ocean and it's covered by sea ice, ocean temperature can't go below minus 1.8 degrees Celsius, which is the freezing temperature of seawater. But the temperature over a layer of even 1 meter of sea ice, temperature at the surface here could be minus 20 degrees easily. Minus 20 degrees Celsius easily. So removing the sea ice leads to a huge warming, and that's one reason why we saw this very strong warming in the high latitudes where sea ice disappeared, for example. Okay, that's the simplest one. So that's mechanism number one for why we expect higher warming in the high latitudes. Okay, what about number two? So suppose we have a balance of the radiative forcing equal to sigma T0 to the fourth. We can use Taylor expansion to write F plus delta F equal to this. Expanding, you get this, which gives you the approximation. The delta F is approximately equal to 4 times T cubed times delta T. And from that we get that the warming is equal to the radiative forcing divided by T cubed. And that gives us a warming that looks like this. If the original temperature is 240, that would be a temperature in the Arctic on a very cold day. Then you get a warming of 1 point something degrees for a given radiative forcing of 4 watts per meter square. And if your original temperature was 300 degrees, you get only half the warming. So in the tropics, the warming you'll get from this balance is half the warming you'll get in the Arctic. Now comes the change to the lapse rate in global warming. And we need to be careful here. There's a lapse rate effect in the high latitudes and a different lapse rate effect in the low latitudes. So I'd like to explain these two first. So suppose we start with 2 parcels at the surface, and they both rise under moist convection, which we covered last week. You remember what happens. There's saturation at some point. You reach the level of the lift condensation level, then the level of free convection eventually, and then you go up and so on and so forth. So suppose we start with 2 parcels with slightly different temperatures, and they're both starting completely saturated with water. If you start with a warmer one, only 2 degrees warmer, because it's warmer and 100 degrees saturated, it has more moisture than the one that started at 25 degrees, right? So this parcel, the orange one, is slightly warmer, but also has more moisture because it started out warming and both are saturated. So as we rise up, there's more moisture to condense, and this would lead to more heating due to latent heat release. So by the time you get up, the warming is much larger than it was originally here due to this effect of the latent heat release. This is the warming difference between the two. At the surface, we started with a difference of 2 degrees. Once we get to the higher atmosphere, the difference is 8 degrees. Okay? So this will play a role in the explanation. Remember what we're trying to explain. In the explanation of why the Arctic warms more than the tropics. So this is what happens in the tropics. The lapse rate, as you warm the surface, the lapse rate becomes less steep. So again, we started with the lapse rate like that. Due to the warming, we shift to the right and make it less steep. Okay? Great. Questions about this? Okay, let me do this again. So I'm describing a situation in the tropics. I have 2 parcels that start at the surface. The blue one is before global warming has occurred. The temperature is 25 degrees. The air parcel is completely saturated. I start raising it up. It will condense, release latent heat. warm as it goes, and therefore it will rise even more. Remember, as while it's rising, it's also cooling adiabatically because of the pressure change. But the fact that it releases latent heat means that the cooling is not as much as it would have been without the moisture. And now I'm after global warming has occurred, 2 degrees warmer in this case. I look at an air parcel as it rises. It has more moisture to begin with because given that it's 27 instead of 25, and given the relation between moisture and temperature, there's more moisture due to the Clausius-Clapeyron relation. So this parcel starts with more moisture and at 2 degrees higher temperature. Now it starts going up. As it goes up, it has more moisture to condense. As a result of that condensation, there would be more latent heat release because there's more moisture being condensed, more water vapor being condensed. So as it goes up, you see a larger warming here than there was in the blue one. And the difference between the two profiles is this. We start with a difference of 2 degrees here. But the excess moisture led to a significant additional warming as this second parcel, the orange one, went up of about 8 degrees by the time we reach the very high atmosphere. Okay. So this is a schematic of what we just talked about. We have a profile in the tropics. The warming leads to a shift at the surface, but then a change in the lapse rate because of this release of latent heat. In the Arctic, the picture is completely different. In the Arctic, today, in most areas in the winter, there's something referred to as an inversion. Inversion is because the temperature increases as a function of height instead of decreasing. The reason it's increasing is that the surface is extremely cold, and that affects the lower atmosphere, so it's really decreasing as you go toward the surface because the surface is so cold. If you melt ice, say, the surface does not remain as cold, and therefore the surface would become warmer. The inversion disappears, and your profile just shifts. So this shift, plus the disappearance of the inversion, means that the surface warming is larger than the warming at the top of the atmosphere. So the difference between these two scenarios is that in the tropics, the high atmosphere warms more than the surface, while in the Arctic, the surface warms more than the high atmosphere. And that would lead to an explanation for polar amplification. Let's take the last step in explaining polar amplification in terms of this third mechanism. So what do we know so far? We know that if there's a certain warming at the surface, in the tropics, the upper atmosphere will warm more, while the Arctic would warm more at the surface than at the high altitude. So now suppose that the warming at the top is the same here and here because it's determined by the change to the emission level and the greenhouse gases and so on. So suppose the warming at the top of the atmosphere, say the emission height, is the same in the tropics and in the Arctic. Right? Remember, now the top warming is the same. We know that this warming is less than what's happening at the top of the atmosphere, while this one is more than what's happening at the top of the atmosphere. So this immediately means that the warming at the surface will be larger than that of the Arctic, and that gives us polar amplification. And it turns out this effect is actually as important as the albedo feedback, surprisingly enough. So we have 3 feedbacks that we came up with. One, the albedo feedback is the most straightforward. The Planck feedback is simple but relatively small, and this is referred to as the lapse rate feedback. It's not a great name for a variety of reasons, but this explains as much as the albedo feedback explains. Of course, the two are very tightly coupled because the disappearance of the inversion has to do with disappearance of ice, and when ice disappears, the albedo is also changing. So these things are very strongly coupled. All of these together give us this effect that we saw before of enhanced warming in the Arctic relative to the mid-latitudes. So we have 3 explanations for that. Okay. We have one more thing that we need to understand today that is really important, and that is stratospheric cooling. These observations, so this is from the most recent IPCC report. You could see, so this is 10 kilometers into the atmosphere, so height in this axis, latitude here. You see warming in the upper troposphere and cooling in the stratosphere. Observed. This isn't model projection. It's what observed. Let me remind you what the projections for the future are. See, whatever warming you're getting in the lower atmosphere, you're getting much more cooling in the upper atmosphere. So it's a very dramatic effect. This is a profile averaged over the tropics, or over the mid-latitudes, I guess. So you see two profiles here. One is 2006 to 2010, so pretty much present day. This is the blue one. And the red one is a projection for 2100, and you can see warming all the way to 20 kilometers, but then very significant cooling. So why is it that we expect the stratosphere to cool in a global warming scenario is what we're trying to understand now. Okay, so the way to analyze this is remember we had an energy balance model of two layers that we did in the context of the greenhouse. So we had an atmospheric layer and a surface layer. We're adding a stratospheric layer now. So let's look at this model a little bit and try to understand what's going on before we see a single equation, right? Okay. So starting with the surface, of course, we have radiation from the sun reaching the surface. There will be some reflection by albedo and so on. I'm not drawing that. So there's shortwave source here. There's also long wave coming from the atmosphere, from the troposphere. This is this arrow. And there's the long wave radiation going from the surface up. So this layer looks just like before. There's one difference, which is now we have a stratospheric layer, and that emits also long wave, and some of it reaches the surface. That's a small difference. Okay. For this layer, previously what we had is heat source from the surface and emission both up and down, if you remember, the 2 epsilon sigma T atmosphere to the fourth and so on, that's this. This time we also have some of the long wave radiation coming from the stratosphere would be absorbed by the troposphere as well. And some of the radiation coming from the surface would not be absorbed here, but would continue up. So it's a slightly refined picture of what we had before. All of these are details. Here's the critical issue here. Some of the shortwave radiation is absorbed by the stratosphere, by the ozone in the stratosphere. That is the reason that in the stratosphere the temperature increases with height, is that it's receiving shortwave radiation and absorbing it in the ozone layer, and that makes it warm as you go up in the stratosphere. So that is reflected by the fact that this solid arrow here is becoming a dashed line because there's some absorption here. Okay, so the idea is just like before. The one huge difference is that we now have shortwave absorption, so solar radiation absorption in the stratosphere by the ozone layer. This will be the reason that the stratosphere will cool as a result of the increase in CO2. We just need to understand why. This looks terrible. Ignore the lower half. You know, it's late in the day, so I'm not writing equations on the board. You have the slides available. Okay, so what do we have? It's a mess, right? Let's try to deal with this one by one. What's this one? What's this?
Solar shortwave radiation.
Shortwave radiation coming from the sun. Now, this is the surface heat budget. You see that the shortwave radiation includes now 1 minus beta. We're removing the part that was absorbed by the stratosphere. This is similar to what you had in one of your problems where the atmosphere with the troposphere was absorbing due to some contamination, all of that stuff, same difference. So this is the effect of the absorption by the stratosphere on reduction in shortwave radiation appearing at the surface. What's this one? Tro is troposphere. This is this layer right here.
The emissivity of the troposphere.
This is the emissivity of the troposphere.
That's downward radiation.
Downward radiation from the troposphere to the surface absorbed by the surface. Next. This is downward radiation from the stratosphere appearing at the surface. This is this arrow right here. So there's really no mystery here, right? Okay. And this is the sink. So all of these are sources of heat for the surface. This is a sink. This is the long wave radiation emitted by the surface upward. That's this arrow right here. All right? Next, this is the heat budget of the troposphere now. So what do we have? What's this one?
Surface up.
Surface up, absorbed by the troposphere. So this is Ts to the fourth. This is the surface heat flux that was absorbed by the troposphere. This is this arrow here. Okay, the next one is the stratospheric long wave radiation absorbed by the troposphere. Okay, and this one is the two orange arrows that go up and down from the troposphere, just like we had it before. Now we're getting to the more interesting and different stuff. So let's look at this one carefully. So what is this?
Wait, why is it a 2? Why is it 2?
This one, why is there 2? Does someone remember why is there 2?
Like the surface can only get one direction, but you to.
That's right. The troposphere emits both up and down. We're thinking of the troposphere as being a thick layer that emits in both directions. So in this very simple approximation, symmetrically. It's not the greatest approximation, good enough for now.
Your definition of simple approximation scares me.
Very good. Fair enough, fair enough. Okay. So what's this now? So this is the heat budget of the stratosphere. What does this term represent? Input from the sun. So we have the S0 divided by 4 is the short wave radiation from the sun. Beta is the absorption of that by the ozone layer. So this beta is the effect of the ozone layer absorbing shortwave radiation in the stratosphere. And now we have a bunch of additional sources. So this one is tropospheric heat flux absorbed by the stratosphere. So this one corresponds to which arrow on the left and on the figure there? What color?
The yellowy orange one. From the troposphere to the stratosphere.
Yes, it's this one right here. Because it's the heat emitted by the troposphere and absorbed by the stratosphere. And that's what we have here. This is emitted by the troposphere because it's epsilon troposphere times T troposphere to the fourth. So that's the heat emitted by the troposphere. And epsilon stratosphere means this is how much of it was actually absorbed by the stratosphere. And finally, the stratosphere is also emitting up and down, so this is the sink. Okay, let's ignore this. It's not important right now. This is how you can solve these equations. It turns out it's just a linear set of equations for the T to the fourth. Never mind. We can ignore that for now. We solve it somehow. And now when global warming happens, all the emissivities will increase because in this very simple picture, admittedly, because of the effect of CO2. So all the emissivities, all the epsilons will get larger. Okay, this is the heat budget of the troposphere. When you increase the CO2, two things are going to happen. One, the emissivity of the troposphere will increase because the emissivity, the long wave emissivity, depends on the concentration of CO2. The higher the CO2, the more emissivity we get. Okay. Also, the temperatures will change. The Ts will change, and the T stratosphere will change, and T troposphere will change. But the effect of the emissivity of the troposphere drops out because all of these drop out of the equation. They multiply all terms. So the sinks and terms, the sources and sinks change together with epsilon troposphere. It drops out. That doesn't make a difference. The only thing that makes a difference in this heat budget is that the temperatures changed. It's very, very different in the stratosphere. Let's see why. As you increase the CO2, the emissivity of the stratosphere increases. So on the right-hand side, the stratosphere will emit more long wave radiation because epsilon stratosphere increased. You know, there's more CO2 in the stratosphere. As a result of that, it will emit more long wave radiation. The emission of long wave radiation depends on the temperature, but also on the emissivity. And the emissivity is increasing, so the sink will increase. The source terms also depend on epsilon stratosphere, this one and this one. So these will also increase correspondingly due to this epsilon stratosphere factor. But there's one source term that does not depend on epsilon stratosphere. This is the shortwave radiation here. So the source terms don't increase with epsilon stratosphere as much as the sink term. Again, the cooling is increasing together with epsilon stratosphere due to the increase in CO2. But the warming components, the source components, don't all increase with epsilon stratosphere because of this term that doesn't change as a result of the change in CO2. So we have a stronger sink term and not as strong source terms. So the net is that we're cooling the stratosphere because of that. We have the source terms. We have the sink term. So again, this is the energy balance of the stratosphere. All of these are source terms. They are sources of heat for the stratosphere. This is the sink term. This is how the stratosphere gets rid of heat. The sink on the right-hand side increases due to the change in the stratospheric emissivity. The sources don't all change because this one does not depend on the CO2 and emissivity. And as a result of that, the cooling increases more than the warming, and that leads to a net cooling effect. Okay? So let's summarize everything and call it a day. I think it's fair to say that there's not much uncertainty in how much surface warming has occurred so far. 1.2 degrees and all that. We talked about warming over land being larger than warming over the ocean. We understand that the deep ocean, it remains cool, and that affects the surface ocean, hence this difference between land and ocean. We talked about hiatus periods as being a natural outcome of the fact that the global temperature would increase and decrease periodically or roughly periodically due to natural climate changes. And then you superimpose on this oscillatory behavior a trend, and you get hiatus periods wherever the temperature wanted to go down. So it really would have been a surprise if we didn't have hiatus periods. So it's not a big surprise. Polar amplification, we discussed 3 different mechanisms for that at length. We talked about how to calculate the equilibrium climate sensitivity from very basic arguments without using any climate models, and you came up with roughly 3 degrees. 3 degrees sounds like a reasonable estimate as far as we can tell. We talked about the delaying effect of the ocean because the cold deep ocean takes a long time to warm up, and this delays the surface warming as well. And we talked about the stratospheric cooling. And I wanted to mention the fact that we already see a stratospheric cooling, even though it's actually complicated because there are many other factors, but that is going to be a good indication that the warming we see in the troposphere is indeed because of CO2 increase, because we also see the expected cooling of the stratosphere. All right. Thank you. See you next time.